congruences, okay, which is something that you've been looking at up to now, especially with John on the cryptography side. So you've been doing arithmetic modulo 26 as a means of describing basic cryptographic schemes on the alphabet. But we're going to make this, give this quite a thorough examination in the number theory side. And so we're going to continue that today. So just to remind you of the definition we looked at on Friday, we're introducing a relation amongst integers, okay, called congruence. So we speak of two integers, or one integer being congruent to another one. And what this means is, well, we've got two ways of looking at it, remember. We've got our initial definition, which says that A is congruent to B. What that means is to say that n divides the difference A minus B. The two numbers, the difference between them, or the distance between them along the number line, is a multiple of n. Okay. And we write this A triple equals sign kind of symbol, but we use that as the congruent symbol. A congruent to B modulo n. But we quickly proved a theorem which gave us an equivalent way to think about it, and in some ways maybe a more meaningful, informative way to think about it. So you could, if you wanted to, take the result of this theorem as the definition of the congruence relationship. It's just an equivalent way of restating it, but maybe one that's more natural. So this says that two integers are congruent. Well, that, in the sense we've introduced just now, what that's equivalent to saying is that if you divide both of the numbers, a and b, by n, if you divide them both by n, they both leave behind the same remainder. So these two remainders that they leave behind, they're going to be equal if a and b are congruent. And these are the kind of standard smallest remainders that we leave behind. So when we divide one integer by another one, so here you're dividing a by n, and here you're dividing b by n, you leave behind a remainder which is somewhere between 0 and strictly less than n. So the smallest positive remainder, sorry, the smallest non-negative remainder that you can leave behind. Okay? So being congruent is the same as having the same remainder after division by n. So you're grouping together, we're regarding as equivalent all integers which leave the same remainder after division by n. Okay? So still recapping last time, we then went on to discuss equivalence relations. Because congruence is an equivalence relation. An equivalence relation is a relation which shares a lot of the same features that the equality relation has. Equality is like a very fundamental relation, lies at the root of all kind of maths and logic, saying the two things are the same. Well, these three properties here, reflexivity, symmetry, and transitivity, these are three important properties that the equality relation has. And they're also shared, but they're also shared by many other relations. Any relation which has these three properties is called an equivalence relation. And we proved last time that congruence is an equivalence relation. Congruence is an equivalence relation. And any time you have an equivalence relation on a set, what the equivalence relation does, if you group together all of the elements that are equivalent to each other, so all these elements, so this is some big set X, all these elements are equivalent to one another. Here's a lot of other elements that are equivalent to one another, but not equivalent to any of those. The equivalence relation produces a partition, okay, which is a subdivision of the overall set into subsets. It's a system of non-empty subsets in such a way that every element of X is in one of these subsets, so nothing is left unaccounted for. And secondly, these different sets in the partition are completely separate. There's no overlap. Okay? So either two elements, either two parts of the partition are exactly the same, or they're completely disjoint. Okay? And this, this agrees with the way partition is used, as we get the example of when one country is subdivided into two or more smaller countries. You know, you don't want to produce bits of land that aren't in any country, and you don't want to produce bits of land that are in more than one country where there's a dispute over the land. So the way partition is used in kind of international agreements is the same way. So congruence is an equivalence relation on the integers. That's what we did last time. So then where we left off last time was we were part way through discussing exercises 4.1. So the first thing I'd like to do today is just to continue in our discussion of these. So what exercise 4.1 is doing is investigating how well the operations that we have on the integers, okay, which are the most important operations are addition and multiplication, how well these operations fit with this congruence relation. And this set of exercises is going to culminate in this final statement here, which says that if you take any polynomial with integer coefficients, now what are a and a prime here? A and a prime are a pair of integers that are congruent modulo n. They both leave behind the same remainder after you divide them by n. They're equivalent modulo n. If you take any polynomial which has integer coefficients, and you evaluate it at a and a prime, okay, you'll probably get different integers, different values, but the values that you get will be congruent modulo n. So evaluating at a polynomial preserves congruence. The two arguments are congruent to begin with, a and a prime, so will the values f of a and f of a prime. So that says that polynomials kind of fit well or play well with this relationship of congruence. Now, polynomials are built up out of, if you think, what do you do when you're evaluating a polynomial? You're multiplying things together and adding them together. Yeah. So last time we proved, so that in the setup to these exercises, we have two congruent pairs, a and a prime and b prime. We saw that if we added a plus b, that was congruent to a prime plus b prime. And similarly for multiplication, if we multiply a times b, that's going to be congruent to a prime times b prime. So we'll just continue. These are the steps for building up properties about addition and multiplication and congruence. So we'll have a look at number 3. So we'll have a look at number 3. A plus c congruent to a prime plus c. So again, we're starting off with the assumption that a is congruent to a prime mod n, and now c is any other integer. So if c is any other integer, the conclusion we want is a plus c is congruent to a prime plus c. And what do we need? In order to make that conclusion, we need to satisfy the definition that n divides the difference a plus c with a prime, the difference between a plus c and a prime plus c. But how could you, well, you see here when you've got these two things here, the c and the minus c cancel. So this is the same as saying a divides a prime, a minus a prime, which is exactly what you get when you interpret the assumption. We're assuming a and a prime are congruent. So I work backwards, but now we read it forwards as the proof. If a is congruent to a prime, the meaning of that, so by definition, the definition of congruence, this means a divides the difference a minus a prime. And we can introduce a plus c and a minus c. We're not changing anything. Same as adding 0. So that's just a bit of algebraic manipulation. and commutativity and associativity of addition and subtraction and so on, but just basic algebraic properties. But then we note that m dividing the difference of these two is exactly the definition that a plus c is congruent to a prime plus c. So the justification for that final step is by definition as well. Okay, so just two instances of appealing to the definition of congruence. Is that okay, everybody? So just interpreting the assumption from the definition, a little bit of algebraic manipulation to get what we want, so that we can then apply the definition to get the conclusion. Yeah, do you have a question there?
I hear what you're saying, but I forgot to put that dash. That differentiation, a differential.
No, this just refers to, so a is a certain integer and a prime is just a different integer.
Oh, so it's like
But
or something.
I could have called it a different letter, but because I want to closely associate it with a, I call it a prime. No, it's just some other integer, could be prime, could be not, some other integer that's congruent to a. Yeah. And in the same way, b prime is some other integer that's congruent to b.
What is congruent?
Well, that was what we went through on Friday. So I mean, congruent is, if you look at the definition at the start of chapter 4. Yeah. I mean, we could have called a prime and b prime different letters, but it's more meaningful to call them a prime because I want to closely associate a prime with a and closely associate b prime with b, and so on. So that's the relationship of this property of congruence. So if you start off with a congruent pair and you add some fixed number to both of them, use the new pairs, you have a plus c and a prime plus c. Those will be congruent. Okay. Now we want a similar result. Number 4 is saying a similar thing, but this time with the operation of multiplication. So we want to show that a times c is congruent to a prime times c. We don't expect this to be too tricky. It should just come from looking at the divisibility statement. Okay? So a being congruent to a prime means m divides the difference a minus a prime. We want to say ac is congruent to a prime c. So we need to reach a divisibility statement, but to bridge this gap, which says that m divides ac minus a prime c. Well, it's not too hard to see what we need here. Here we just need to multiply the thing we're dividing by c. Are we free to do that? Yeah, it'll be something in Theorem 2.1. When we first introduced the divisibility relation all those weeks ago, we proved a Theorem 2.1 which ran through a number of basic properties of divisibility. So one of those will be that if you have some number divide some other number, it also divides any multiple of it. In fact, it's an example of part 3 of Theorem 2.1, which in general talked about forming any linear combination of two numbers where you've got, yeah, so it's Theorem 2.1 part 3, which in general talked about divisibility being preserved under forming linear combinations. So this is an example of this. M divides this one number, so it's going to divide any multiple. Okay. So again, just using the definition of congruence. It's a step to a divisibility statement, working on the divisibility statement until you get the thing which is the definition of the congruent statement that we want. Okay. And the property of congruence, that this implies this, comes from stepping down to the divisibility statement and working with what we know about divisibility. Okay. So that was number 4. So we're nearly there. Number 6, about the polynomial result. Now number 5. For every k in z, well, we have to be careful about that. We haven't really said what raising an integer to a negative power would mean yet. I guess we have to wait a little bit. until we think about that. But if we're going to be talking about polynomials, well, we really only need number 4 there for positive k. So let's just talk about positive k. Well, here we want to say that a to the k is congruent to a prime to the k, modulo m. Then we already know that a is congruent to a prime. A is congruent to a prime. Yeah, that's the assumption up there. Do we need to go down to divisibility statements? Do I need to go to step down to divisibility and then use properties of divisibility? Well, not really, because powers, raising a to a power is just repeated multiplication. So I can actually, but I've already proved the basic property of how multiplication preserves congruence here in number 2. If a was congruent to a prime and b is congruent to b prime, when you multiply a and b, you get something congruent to multiplying a prime and b prime. So here, I can get this. We just use repeated applications of part 2. Repeated applications of part 2, where we've got a and a prime as one pair, so I'm using b as just a again, and b prime as a prime. So it's the special case of number 2, where b is equal to a and b prime is equal to a prime. Because then number 2 says a squared is congruent to a prime squared. Just repeat the application of that to get a cubed is congruent to a prime cubed. And then a to the power 4 is congruent to a prime to the power 4. Okay. So, I mean, if you really wanted to do it formally, you could set it up formally as a proof by induction. Proof for any exponent k, a to the power k is going to be congruent to a prime to the power. But I think we get the idea. You just repeatedly apply that that result about products. Okay. So I think we're ready now to prove 6. Well, 6 really, I mean, really, the proof of 6 is parts 1 to 5. So we really just need to spell that out, make that clear, and just check that we don't need anything else really. Or it's just going to be repeated applications of parts 1 to 5. So we should give ourselves a general polynomial. We're talking about a polynomial with integer coefficients, so it's going to look something like, call the coefficient ci, x to the power I, and this is going to be summing over I equals 0 up to some upper limit n, say. Okay, so that's a general looking polynomial with integer coefficients we want this polynomial to have. So the ci's are integers. And yeah, we want to evaluate f at a and evaluate it at a prime. Well, when you look at f evaluated at a, you get the sum from I equals 0 up to n of ci times a to the power I. Now, each a to the power I is congruent to a prime to the power I. Okay? That was proved in part 5. And each time you have two congruent things and multiply them by some same fixed coefficient c, you should think of this c here in part 4 as being one of these coefficients ci. If you've got a congruent pair and multiply them both by c, they remain congruent. The new integers you get remain congruent. Then you got a bunch of congruent things, and then you're then going to add them together. But again, the congruence is going to be preserved. Okay? So what can we say here? We could say that this is congruent to summing I equals 0 up to n of ci times a prime to the power I, since each ai is congruent to a prime to the power I, part 5, which in turn implies that multiplying ci by a to the power I is congruent to ci a prime to the power I. So this first part by part 5, this part by part 4, and then you just need a load of part 1s, don't you? This is congruent to this. If you load of things here, and each of them is congruent to their partner over here, or when you sum all of these, that's going to be congruent to summing all of these. And this is f of a, this is f of a prime. So we can just quote it in one step. Congruent to this modulo n using parts 1 to 5. So that tells us now that polynomials fit well with these, with the congruence relation. Okay? Now, well, this will be a bit of a theme for the next part of the unit. And if you look at the next, we've got 2 chapters coming up in a while, and after a chapter or 2 in between. 2 chapters which look at this, the theory of the solution of polynomial, not polynomial equations, but polynomial congruences. So when you consider polynomials as not acting on integers, but acting on congruence classes of integers, looking at the theory about the existence of solutions to those. Because the result of part 6 now tells us that we can give a valid definition to the idea of the polynomial acting on the congruence class. Okay? Because the polynomial takes, well, not the same value, but the different values it takes on different numbers that are congruent to one another, all those different values it takes, they're all congruent to one another. So a polynomial sends one congruence class to another. Okay? You can find out what the value congruence class is by evaluating the polynomial on any representative in the original congruence class and looking at the congruence class of that value. Okay. We've then got a theorem 4.3, which I wonder, should we look at the proof at now, or no? I think I'm going to skip over that for the moment. I'll leave you to read. I'll return to it either in the tutorials or in the next lecture. The theorem 4.3 looks at the issue of cancelling congruences, sorry, cancelling factors from a congruence. But to make some progress, I'd like to get up and look at the definitions of the modular arithmetic groups. Okay. So if we come forward to section 4.4, and there's other material there which I think will relegate to the tutorials as well. We'll be investigating it shortly. So I'll draw an example to help us think about this, what we're going to look at now in theorem 4.4. Draw a large picture. We're going to think of the integers modulo 10. So think of this, the congruence relation modulo 10. So So this is a relation on the integers. Congruence is an equivalence relation, so it's going to partition all of the integers into 10 subsets. 2, 3, 4, 5. Okay, so there's all of the integers partitioned into 10 subsets. And remember, two integers are congruent to one another if they leave the same remainder after division by 10. So 0, the integer 0 is going to be in one of these subsets. And the things that are there with it are the other integers that also leave a remainder of 0. So in no particular order, there's a bunch of integers that are also congruent to 0, modulo n. 10, 20, 30, minus 10, minus 14, so okay. No particular order. And there's an infinite number of them. Okay, all the multiples of 10 are in. Somewhere else is going to be the integer 1, and sitting in with it is going to be 11, 21, minus 9, and so on. Okay, 101. All these other numbers that also leave a remainder of 1 behind when you divide them by 10. Okay? So 2 is going to be in here somewhere, and it's going to have 12 and 22, etc. And all the negative numbers as well, minus 8, minus 18, etc. When you divide minus 8 by 10, it goes in minus 1 times and a remainder of 2. The remainder is always non-negative. 3 is going to be somewhere, and that has 13 and 23. 4, that was 14, 24, etc. 5, get the picture, 15, 25, etc. 6, 16, 26, etc. 17, 27, etc. Just 2 more to do. 8, 18, etc. 9, 19, etc. Okay? So every integer is in there somewhere in one of these sets. Okay? Because any integer, when you divide it by 10, it leaves a remainder somewhere between 0 and 1. Okay? So this divides up the infinite number of integers into these 10 sets, and there's a natural set of representatives we could use. Okay. Okay. If we just use the smallest positive remainder, which lives in each of these congruence classes, okay, that's a nice, sensible set of representatives that we could use to represent the integers modulo 10. Okay. So there's some special notation used. So when we write square brackets A, now if you want, we could put a subscript 10 here, but let's just think that it's understood we're working modulo 10. We understand that we're working modulo 10. Then this square bracket notation stands for the congruence class of A modulo 10. Okay? It's the set of all integers B such that A is congruent to B modulo 10. Okay? So this set here is the congruence class 5. This set here is the congruence class 3, and so on. Okay? Now, what the results of the last set of exercises showed us was that we can actually think of the operations of addition and multiplication now as acting on, not on individual integers, but acting on the congruence classes. Okay? Acting on the congruence classes themselves. What do I mean by that? Okay, we all know how to add integers, how to add a pair of integers. But now we want to speak of adding congruence classes of integers. Okay? So here I've got 2 congruence classes modulo 10. So 2 of these subsets. I want to add them together. And there's an actual definition to that. Well, I just choose one representative from the first one representative from the second one. I add them as integers. So this plus here is just the plain old-fashioned plus, adding integers together. So you add the representatives, and you then look at which congruence class you end up in. Okay. This definition defines this new operation plus as an operation on Z10. So Z10 is the name given to this view of the integers. Viewing the integers is split up into these 10 congruence classes, modulo 10. We call that 10 Z with a subscript 10. This equation here gives you the definition of this operation of addition on Z10. And we can also multiply the congruence classes in the same way. Well, we could put in the multiplication symbol there, but I mean, we normally don't. Save space. And the definition of multiplying two congruence classes together is to take a representative from the first one, a representative from the second one, multiply them together, and look at the congruence class that you end up in. Okay? But now we need to, whenever you introduce new operations like this, you have a worry in your mind, because these representatives are not unique. So for instance, if I want to add these two congruence classes, I want to add the congruence class of 7 to the congruence class of 2. So I add the representative 7, 2, and I get 9. So I know that I'll end up in this congruence class over here. So I add this congruence class plus this congruence class seems to be this one. But I have to check that that was well defined, because there's nothing that special about 7. Equally well, 27 could represent that congruence class. Equally well, I could have chosen 27 and minus 8, say. I could have chosen 27 to represent the congruence class of 7 and minus 8 to represent the congruence class of 2. I could add those two then, 27 and minus 8, just add them as plain old integers. You get 19, which is different to 9, but of course, 19, you still end up in the same congruence class that you landed in before. Yeah. Now, what part 1 that we proved on Friday, it said that no matter what you take from here, and no matter which representative you take from here, you will always end up in this congruence class over here. Because to do this evaluation here, you see there's an infinite number of choices for representatives from this congruence class, an infinite number of choices of elements to represent this one. So you have to be sure that because you're basing the definition of this new operation on evaluating an operation using representatives from here, you have to worry and check that it's well defined, that no matter what choice of representative from here, no matter what choice of representative from here, you always land up in the same congruence class, that the operation is well defined. Part 2 did the same thing, but for the operation of multiplication. So if I want to multiply the congruence class 5 by the congruence class if I want to multiply the congruence class 5 by the congruence class 3, sorry, I was having a think there, because you'll notice something funny happening. Well, 5 times 3 is 15, which sends you back to this congruence class. But equally well, I could have chosen different representatives. I could have chosen 15 and 3. When you multiply those two together, you get 45. But 45 is again back here. So you always get back to the same result. Okay? So now we're in the situation where when we talk about congruence modulo 10, for instance, we've got this new set called Z10, which is the set of congruence classes. And we've got these two operations, operation of addition and operation of multiplication. Now this is the framework of group theory. Anytime you have a set and an operation on the set, an operation on the elements in the set, which gives you new elements in the set, that's the setting for group theory. Okay? And such a system, the system of the underlying set, here Z10, partition of Z modulo 10, that set, together with one of these two operations, that may be a group. Okay. So, and there's a lot of theory, a lot of algebraic theory built up about groups. So groups are nice situations where you've got a set and an operation, and where the operation satisfies certain nice properties of the set. And it's a good way to view these situations. And group theory tells you or investigates all the features of that relationship, of how the operation behaves on the set. Okay? So it can help us in our discussion of number theory to look at that. Okay, so these are called the modular arithmetic groups. There's an additive one using the addition operation and a multiplicative one using the multiplication operation. So let's just remind ourselves. So you would have met this in first year, briefly, in the maths fundamentals. Let's just remind ourselves of it again. So a group is a system where you've got a set and an operation on the set. So here, when we're just speaking about it in the abstract, we'll use the asterisk symbol to represent the operation. So asterisk could be this plus, or it could be this multiplication. Okay. Situation where you've got an operation on the set. And a group is where this pair, the set and the operation, satisfy these nice properties. Now, these properties will be familiar to you, familiar concepts. First of all is a closure property, which says that when you take elements A and B from the set, you operate them together, A star B. I'll normally read this as A multiplied by B, but it could be any operation. But A multiplied by B gives you another element back in the set. So it's a closed system. You don't hop outside the system by taking products. The thing must be associative in order to be called a group. Okay, associative is a very basic property shared by almost all the mathematical operations you've considered up to now. So any way of evaluating the triple product A star B star C, well, the two different ways you could evaluate the pairwise products will both lead you to the same answer. Thirdly, there must be this special element around called an identity, such that when you multiply any element by the identity, it leaves the other elements unchanged. And fourth, we must have inverses for the operation. So given any element, there must be another special element called A inverse, such that when you multiply them together, you get back the identity referred to in property 3. Okay. So any system that satisfies that is called a group. So do we have groups of where we look at a partition of the integers with respect to some modulus and one of these operations? Well, we do in the addition case. There's no problem in the addition case. So if we write Zn for the set of congruence classes modulo n, which we did here for Z10, but we could do it in general for any modulus, we normally use the integers 0 to n minus 1. In that example, we use 0 through 9. We normally use those as the standard representatives of the congruence classes. So those are the elements of the group. Then all four of the group properties, the group axioms, the ones we just looked at, they're all satisfied in the case of one of these modular Z10s and the operation of addition. Okay. And the system's certainly closed. You add to these congruence classes, you again get a congruence class of an integer. The congruence class of 0 is the identity. Okay. You add the congruence class of A and the congruence class of 0, you again get the congruence class of A. And there are inverses. The inverse of the congruence class of A is the congruence class of minus A. Okay, because when you add those two together, you get the congruence class of 0. Okay. So we do get a group in the addition case. Now, anytime you've got groups, you can also draw an operation table for the group, where you put the elements as headings on the rows of the table and columns of the table. And the entry inside the table, well, the entry in column in row GI and column GJ, the entry there in the intersection of those two is GI star GJ. So GI on the left and GJ on the right. You have to have this, you have to take care what the ordering is in cases where the operation is not commutative. Okay, but operation and addition are always commutative. So you just need to remember that the entry inside this Cayley table is GI star GJ. So the row index times the column index. Well, here's a simpler, smaller example than Z10. Here's the Cayley table for the partition on the integers modulo 4, Z4, under the operation of plus. Okay, now we'll dispense with the square brackets. So we're just leaving the square brackets, leaving them behind, because otherwise just everything would have a square bracket around it. It would just be a bit messy on the page. So we'll just drop the square brackets by convention, but you still think that they're there. So these aren't the numbers we're adding, they're the congruence classes. Under this definition of addition of the congruence classes here. So, so you can look at some of the additions there. They just, confirm that they look right. Sorry, this is distracting. So we'll look at some of these additions. 2 plus 1 is 3, fair enough. 2 plus 2 is 4, and that's 0 because, well, the congruence class of 2 plus the congruence class of 2 is the congruence class of 4. But 4 is in the congruence class of 0. 0 is the representative of the congruence class of 4 when you're talking modulo 4. 3 plus 3 is 6, but of course that's equal to 2. When you interpret, you're talking about the congruence class of 6. That's the congruence class of 2. So if these are the representatives we're using for the congruence classes, 0 through 3, then all of the entries inside the table are sum of 0 through 3. You also notice here that, well, because you're talking about addition, each time you're adding one on, so each row is just the row above it shifted one place to the left. Each row is the row above it shifted one place to the left, and that pattern continues. If you look at any other modulus, Z5 or even Z10. Now, so that's all very well for addition. What's more interesting, and since we're in number theory and we're interested, we've been talking so far about divisibility in the prime numbers. Okay, so that's all really to do with the operation of multiplication. So really we're interested in the multiplicative group on Z10. But here now, the idea of the existence of inverses becomes an important question. Remember, any group has to have inverses for each of its elements. Okay? The inverse of an element is the other special element such that when you add it to A, you get back the identity. Now, for the operation of multiplication, the identity is the congruence class of 1, isn't it? Okay? The identity element for multiplication on the integers is the element 1. So when we're looking for inverses in the multiplicative group, you're looking for the inverse of A, you're looking for another congruence class such that when you multiply it by A, you get back to 1. Now, there wasn't a similar problem in finding integers under addition because finding inverses under addition because there the inverse was quite obviously minus A. And minus A was again an integer. However, we can't make the similar statement that under multiplication, say if we're talking about multiplication modulo 10, what's the inverse of 2? I mean, you're kind of tempted to say it's equal to a half. What's the inverse of the congruence class of 2 under multiplication modulo 10? You're kind of tempted to say that, except you can't say that. Because we happen to find congruence classes of fractions. In fact, we want to avoid talking about fractions entirely, really, in this. We're just focusing on the integers. So, really the question is there an integer A such that 2 times a is congruent to 1 modulo 10? Question. If there is, then this a represents the inverse of the congruence class of 2. Now let's choose another example. Let's choose an example 3. So if you ask a similar question for 3, is there a b such that 3 times b is congruent to 1 modulo 10? So what's the answer? Is there an integer b such that when you multiply it by 3, you get 1 modulo 10? 3 times 7 is 21. 3 times 7 is 21, which is congruent to 1 modulo 10. So what that means is the inverse of 3 is being understood modulo 10. The inverse of 3 is 7. But you might search for this a up here, but you're never going to find it. Okay? There is no integer a. So when you multiply it by 2, you get something congruent to 1 modulo 10. So sometimes elements have inverses modulo 10. Sometimes they don't. And it's not just random. It follows a very clear pattern using something we've studied up to now. And the condition is based on the greatest common divisor. So I'll just end with this, and we'll pick this up next time. So the question of when a congruence class A has an inverse with respect to multiplication, it has it if and only if the greatest common divisor of the integer you're talking about and the modulus is equal to 1. So the only times they have these inverses are when A is congruent to, when A and N are co-prime. Now we'll pick this up and continue with this next week in the lectures. Okay.